Okay, so let's continue with our chapter direct current circuits. Okay, so in this video, we're going to talk about what is actually a Kirchhoff law. So we have our Kirchhoff law. So Kirchhoff law consists of two parts. So for the first one is actually Kirchhoff's law. Okay, Kirchhoff's law. And another one is actually describing the Kirchhoff second law. So the Kirchhoff's law is actually describing the current. So this is the current. As for the second law is actually describing the potential difference inside the circuits. Okay, so let's proceed to one by one. So let's proceed to the first law, which is the Kirchhoff's first law. Okay. So what is actually Kirchhoff's first law states? Okay. So the Kirchhoff's first law actually states that the sum or the total, the sum of the current entering the junction is equal to the current leaving the junction. So that is what Kirchhoff's law stating. Okay, so consider I have my circuits. Okay, so this is my circuits, and this is my wire, and this is my consider this is one of the part of the circuits. So consider this is the point where the current is going to separate. Okay, so let's say I have my first current, so I consider this current as my I1, and this is my I2, and this one is my I3, and this is my I4. So the Kirchhoff's law actually tells us that the current which is about to enter the junction is actually equals to the current to those current that is already or I can say that about to leave the junction. So I can conclude that my I1 plus I2, so this is I2, sorry, and my I1 plus I2 is equal to the I3 plus I4. So that is the principles that what the Kirchhoff law stating. Okay, so this is the concept. Okay, so if I derive this equation, so what about I just move this I3 and I4 to the left side? So what I get for this equation, which is I1 plus I2, so I3 and I4 if moved to the other side will be negative. So negative I3, negative I4. So what I get is actually 0. So I1 plus I2 minus I3 minus I4 is equal to 0. So this is actually tells that the sum of current, whatever entering or leaving the junction, so the sum of the current that exists inside the circuit is actually equals to 0. So this is the concept what is Kirchhoff's law means. Okay, so the sum of the current, so the sum of the current inside the circuit, okay, whatever entering or leaving the junction, the sum of the current inside the circuit is equal to 0. So this is how we define the Kirchhoff's law. Okay, so another explanation for this, why the sum of the current inside the circuit is equal to 0. This is because our Kirchhoff's law. So this is actually proving us that the Kirchhoff's law is actually obeyed. Okay, so Kirchhoff's law is actually obeys principle of conservation of charge. Of charge. So when current is entering the junction, it's equal to the current that leaving the junction. So no charge loss or no the magnitude of current flow does not reduce. So this actually proving us that the Kirchhoff's law is actually obeys the principle of conservation of charge. So no charge is lost. So this principle is actually obeyed. So this is how we define the Kirchhoff's law. And what about the Kirchhoff's second law? So okay. So the Kirchhoff's second law, as I said that the Kirchhoff's second law is describing the potential difference inside the circuit. So the Kirchhoff's second law states that states that okay, so the sum of the sum of okay the sum of the changes in electric potential, or I can say that the change in electric potential is potential difference, but we commonly write it as the change in electric potential. Okay, so the sum of the changes in electric potential inside the circuits is actually equals to 0. So this is what the Kirchhoff's second law defines. So I can say that in an easy expression, so the sum of the potential difference or the changes in electric potential at every not every point in one complete circuit or in a closed loop is actually equals to 0. So this is what Kirchhoff's second law defines. Okay, so okay, actually I missed something inside this sentence. The change in electric potential inside the closed loop. Okay, so inside the circuit is actually not so accurate. So inside the closed loop, okay. So the closed loop is actually defining the complete circuit, or and we can say that in the complete circuit. So it is better for us to write the closed loop. So the electric potential inside the closed loop is equals to 0. So this is how we define the Kirchhoff's second law. Okay, so the closed loop, of course, the object is must be written. The closed loop of the circuits is equal to 0. So this is the Kirchhoff's second law. Okay, so the Kirchhoff's second law, the Kirchhoff, as we said that the Kirchhoff's first law is actually obeying the principle of conservation of charge. So as for the Kirchhoff's second law, basically the Kirchhoff's second law will obey principle of conservation of energy. Okay, Kirchhoff's second law obeys principle of conservation of energy. So the potential difference in a complete circuit is actually equals to 0. Means that no energy loss during the current is flowing through a resistor or other batteries. So the potential difference produced inside the circuits, the total potential difference that produced inside the circuit is actually equals to 0. Means that no energy is lost, or I can say that no heat is lost to the surroundings. So this actually proving us that the the circuit is actually, or I can say that the Kirchhoff's second law is actually obeys the principle of conservation of energy. Means that the energy is conserved. Okay, so this is how we define the Kirchhoff's second law. Okay, so let's move on to some derivation. So based on the Kirchhoff's first law and the Kirchhoff's second law, we're going to find out what is the arrangement of the resistor, of the resistance of the resistor, arranged in series or in parallel. So although we know that the potential difference, the resistance, the arrangement of resistance in series, both series and parallel are okay. Okay, how should I describe this? Okay, let me just write down the topics. So using the Kirchhoff's first law and the Kirchhoff's second law, so in a short expression, I just write it as Kirchhoff. Okay, so Kirchhoff's law. To derive the formula for the resistance of the resistor, for the resistance of the resistors. Okay, connected in series, connected in both series and parallel. Okay, so this is our subtopics. So based on, okay, so let's move on to the first one. So let's look out for the series first. Okay, so in series, we know that the series, the arrangement for the resistor in series is actually equals to the total resistance is actually equals to the first resistor plus the second resistor and the third resistor. Okay, so we're going to prove that how is this possible? Okay, based on the Kirchhoff laws that we learned just now. Okay, So in series, we actually know that the current flowing in series is actually the same, which is the total current is actually equals to the first current, equals to the second current, and equals to the third current. So I consider all this current as I. Okay. So as for the potential difference, the potential difference is actually equals to the V1 plus V2 plus V3. So this is the concept for the arrangement in series, arrangement for the electric circuit in series. Okay, so based on the Kirchhoff's second law, we know that the Kirchhoff's second law states that the sum of the currents, sorry, not the current, the sum of the changes in electric potential in the circuit in or in a closed loop is actually equals to 0. So based on this principle, we're going to prove that how is it possible for the resistance, the total resistance which arranged in series is equals to the R1 plus R2 plus R3. So since the change in electric potential is 0, so hence I can say that, okay, so this electromotive force, so this electromotive force, as we said that from the previous video, we know that this E means the potential difference of the battery. Okay, so consider I have a battery inside a circuit. So I have a 3 resistor which arranged in series. So starting from the battery, so the battery after passing through the first resistor, so the first resistor we need to minus IR1. So IR is means that the potential difference across the first resistor. Okay, so as for the second resistor, which is IR2, and same goes to the third resistor, which is IR3. So the sum of the potential difference is equals to 0, of course. So this E equals to IR1 plus IR2 and finally plus IR3. So if I factorize this I, so what I get is actually R1 plus R2 plus R3. So this E over I is equals to R1 plus R2 plus R3. Okay, so E over I is actually equals to the V over I. So V over I is actually equals to my total resistance. So we have proved that the arrangement of resistor which arranged in series is actually equals to R1 plus R2 plus R3. So this is how we um, prove this formula using the Kirchhoff's second law. Okay, so this is for the series. So what about the parallel? So we know that the arrangement of resistor in parallel circuits is actually equals to 1 over RT equals to 1 over R1 plus 1 over R2 and finally plus 1 over R3. So we're going to prove that how is this possible? Okay, so remember from the previous chapter, we learned about the arrangement of parallel circuits. So the current is actually equals to I1 plus I2 plus I3. As for the potential difference, the total potential difference is actually equals to V1 equals to V2 and equal to V3. So I can consider this one all potential difference is actually equals to V. So this is the concept that the basic concept that we actually need to know. Okay, So I can use the Kirchhoff's law. So the Kirchhoff's law tells us that the sum of the current that enter or leaving the junction is actually equals to 0. Or I can say that the current that entering the junction is actually equals to the current that leaving the junction. So this actually same as the meaning for the sum of the current inside a closed loop is actually equals to 0. Okay, so based on the formula that we learned just now, this one. Okay, so we're going to use this formula as our example. Okay, so let me think about the examples. Okay, so based on this, so the IT minus I1 minus I2. Okay, so I think um, not so accurate to written in this form. So we just use the formula just now. So the IT, so consider the current is about to move in 3 directions. Okay, so consider this is the junction, and this is our first current, and this current is about to split into 3, and which is I2, and this is sorry, this one I should write it as I total, which is more easier for me to refer, and this is I1, and this is I2, and this is I3. So IT, if this total current split into 3, so what I get is actually IT is equals to I1 plus I2 plus I3. So this is the concept. Okay, so based on V equals to IR, I is equal to V over R. So what I get is actually V over R1. So V, we know that the V is actually the same, whatever which junction. Okay, so this is equals to V over R1 plus V over, okay, so this is V over R2, and this is V over R3. Okay, so if the circuit is in parallel, the potential difference is all the same. So this potential difference I can factorize it out. So what I get is actually in the bracket is actually 1 over R1 plus 1 over R2 plus 1 over R3. Okay, so this V moves to the other side. So I over V, I total over V. So this is same. So I over V, what we get is actually 1 over R. So I prefer to write it as 1 over RT. So the total resistance is actually equals to 1 over R1 plus 1 over R2 plus 1 over R3. 1 over total resistance is equals to 1 over R1 plus 1 over R2 plus 1 over R3. So we have proved that the arrangement of the resistance in parallel is correct. Okay, so I think we've done for the derivation. So let's move on for some exercise. So in this exercise, we are going to learn how can we find out the um, current or the potential difference across 2 points. Okay, based on the Kirchhoff law that we learned just now. Okay, so for the question 1, so consider I have my circuit which is arranged in series. Okay, so this is the wire, and this is the first resistor, and I have my point X here, and this is my second resistor, and this one is the second battery. And okay, I just simply draw, and the scale is actually not accurate, and this is my point W. Okay, so we get the third resistor at here, and finally the final resistor will be here. And okay, and connect it all. So there's another point, which is the point Y, which is here. And for the first resistor, we have the 15 not resistor. The first battery is actually 15 volts, and the first resistor is 30 ohm, and the second 40 ohm. Okay, for the second battery we have 20 volt, and for the third resistor is 60 ohm, and finally the final resistor will be 70 ohm. Okay, so for the first question, so this is the direction of the current after total up all the electric components that exist inside this circuit. Okay, so okay, I think I just erased. Okay, never mind. I just write it here. So find the for the part A, find I. So we know that if the circuit is arranged in series, the current at every point is actually the same. Okay, so what we need to use is actually the Kirchhoff's second law, since the electric potential are different at all points. Okay, so the sum of electric potential, the change in electric potential, is actually equal to 0 in a closed loop, of course. So I think I just start here, the second battery. Okay, so 20 minus 40i minus 30i. So 30i, 40i means the potential difference across those resistors. Okay, so this is the first and this is the second, and we came across the first battery. Okay, so the first battery is actually 15 volts, minus 15 volts. Okay, so came across the third resistor, which is 70i minus 60i. So the all minus all, what we get is actually the 0. Okay, so let me just write it down. Okay, so this is 20 minus 15, so what we get is actually 5. So the 40, so if I combine all, negative 40, negative 30, minus 70, minus 60, so what we get is actually the 200i. So this 200i is actually moved from the left to the right. Okay, so this I equals to the 5 over 200. So what we get is actually 0.025 ampere. So I can conclude that after combining all the electric components inside the circuit, so what I get for my current is actually 0.025 ampere. Okay, so based on, of course, based on the direction of the current flowing. Okay, so I think we have done for the part A. So let's move on to part B. So the part B, find the electric potential, find the change in electric potential from X to Y. So in the diagram, there's actually point X and point Y. So the question is actually asking what is the change in electric potential across the point X and point Y. Okay. So in this situation, we actually have two choices. Okay, for the first choice, we can move from here to here. Of course, the point must start from X. Okay, so this is the first choice, from X to Y. As for the second choice will be from here to here, which is this will be considered as anti-clockwise and this will consider as clockwise. So this clockwise direction is actually opposing the direction of our current. Okay, so as for the direction of this anti-clockwise, so this anti-clockwise is actually same direction as our current flowing. Okay, so what I choose is actually this one, the anti-clockwise direction. So if I about to count the electric potential across X and Y, so what I get is actually came across the first resistor, which is 30. Okay, so negative 0.025 times the 30. So negative indicates the negative potential difference across the resistor, as we discussed from the first chapter. Not first chapter, sorry, from the previous video. So the the flow of the potential difference is actually flowing from the high region potential difference to the low region electric potential. Okay, so this is negative. So came across the first battery. So this battery is 15 volt. So since the current flowing is opposing the direction of the battery, which is this point has the lower potential and this point has the higher potential. Sorry, I think this is my mistakes, and this is the higher potential to lower potential. So the lower minus the higher will get negative. So this is negative 15. Okay, so moving from here, and finally we approaching the second resistor, and after this second resistor we have already arrived the point Y. So this second resistor, so what we need to do is actually minus 70 multiplied by 0.025. So this is the change in electric potential across X and Y. So if I calculate, so what I get is actually negative 17.5. So this is volt. So I can conclude that my electric potential across X and Y is actually 17.5 volts. Okay. Alright, so we have done for the first questions. So let's move on to the second questions. Okay, so I think we stop here now. Stop here first. So we'll discuss the other questions from the in the next coming video. So I think we stop here now. If there is any question need to be asked, please comment below this video. So I'll see you next time. Thank you. Bye.